All right, this is the simple harmonic motion notes for on-level physics, and we'll get right into it. We divided our notes into 4 sections on both sides of our paper. One side should have 2 sections for vocabulary, and these are the 6 vocabulary words that go in those 2 sections, so 3 and 3. And then one section should be period versus frequency, and another section should just be example for period frequency. If you flip it over to the other side, you should then have it as pendulums, and inside that pendulum, that pendulum square, you're going to have restoring force and period information about a pendulum. Then you're going to have an example. You're going to have 2 examples for the pendulum in another square. Then the third square on the back should have springs, and you're going to have Hooke's law and period for springs in that square. And then you're going to have a square that is for examples of those 2 things for a spring. All right. So when we're talking about simple harmonic motion, this is actually a concept that we're going to cover for the remainder of the school year. So we'll have spring systems and pendulums, which are in this specific unit. Then we'll do circular motion at the very end of the school year, and then we'll do waves, which will be sound, light, and pressure. We don't talk as much about pressure waves, but pressure waves really are just a specific form of a sound wave. So we do talk about sound and light specifically this semester. So definitions to go in your definition square, you have periodic motion, and periodic motion is really just when a vibration or an oscillation, which is a movement, repeats itself over and over and over again, and it goes over the same path. Simple harmonic motion is really just a specific form of periodic motion where there's a restoring force that's proportional to the distance from the equilibrium position. Equilibrium positions are just considered one location. So the further you move away from that single location, the more force it's going to take to move it back to that. So that creates simple harmonic motion. Amplitude is the displacement, and remember that's a distance value in a certain direction, and that direction is from an equilibrium position. And it is a measure of energy of an oscillator. It is actually, so for example, when we talk about sound, the amplitude is how loud things are, so it's how much energy it has. When we talk about pendulum, the amplitude is an angle. Okay, so that's a different unit value because it's in degree mode, whereas amplitude, like a sound wave, is meters because it's a height. So it does, but it measures how much energy it is, and so the higher the amplitude, the more energy it has. Equilibrium position again is that center of motion position, and it's the place at which there's no forces really act on restoring it, because that would be where it's supposed to be. So if it's at rest, that's where it is. Like for a spring system, when you stretch it, before you stretch it, wherever it's sitting, that's its equilibrium position. And when you stretch it, it comes back to that equilibrium position. So then we have displacement, and displacement again is the distance between the center or the equilibrium position and any location of the wave at any time. All of these are types of waves or simple harmonic motion. It creates a sine wave, and so it's any location on that. But displacement's really just directional from the equilibrium position. Restoring force is the force exerted on the medium to bring it back to the equilibrium position. So if it's a spring, it's to bring it back to its rest position. If it's a pendulum, then it's to bring it back to the rest position, which would be straight up and down, like a swing set. And so yeah, those are different types of restoring forces that'll take place to do that. All right. These are just some visual aids. So again, the pendulum is going back and forth, and the equilibrium position's in the middle. So we could talk about its amplitude being an angle, or we could talk about its displacement off the center line. So all of those things work. When we talk about simple harmonic motion, it really is a sine curve. Everything it creates, amplitude's its height. We have its displacement, which could be anywhere on these lines. The equilibrium position would be the center line right here. And then we'll talk about what a period is here in just a minute. So relating period and frequency is period versus frequency. So period is the time required for one complete cycle, so it is in seconds, and then frequency is the number of complete cycles in amount of time. So again, it is it's measured in something called a hertz, and hertz is really just seconds to the -1, or 1 over a second. So the key thing about this is that period and frequency, regardless of what we're talking about, is always the same definition, where period is the time for one and frequency is the number of in a certain amount of time. So they are inverses of each other because of their units, but another way to write the formulas, we can say they're F equals 1 over T, or T equals 1 over F, and the lowercase f being frequency and the capital T being period. We could also say that their formulas are the, we could take the time divided by the number of to get the period. We could also take the number of and divide it by the time to get the frequency. So those are other types of definitions you could have for those two, or formulas, noticing that they're really just reciprocals of each other. And yeah. One of them that you're most familiar with frequency would be like revolutions per minute, RPMs, for cars. So that's the number of cycles that the cylinder goes through in a certain amount of time of a minute. So that's something that you might be familiar with when we talk about frequencies. So an example would be Terry jumps up and down. This goes in your example on the front side of your notes. Terry jumps up and down on a trampoline with a frequency of 1.5 hertz. What's the period of Terry's jumping? So frequency is 1.5 hertz, and our period is 1 over the frequency, and so we would do 1 divided by 1.5 hertz, which would give us 0.67 seconds, and that would be our period. Okay, we talked about pendulums and their restoring forces. So actually I want to pause right there. I'm going to go ahead and stop this video, and that will just be the front side of your notes.